Hi, my name is Gabel. I work for an Israeli company called Wix. We do have offices in Vilnius, and yes, we are hiring, and that's all I'm going to say on the subject. Our booth is next door. Thank you very much for coming. I'm going to try to waste your time gracefully over the next 45 or so minutes, and maybe, you'll even learn something. Before we get started, a bit of full disclosure. This is going to be a talk about CPUs, and I'm far from being kind of a subject matter expert. So everything I say may be inaccurate or oversimplified. I could be wrong in a few cases. Feel free to call me up on it. If there's any heckling or questions or whatever, feel free to raise your hands. Hopefully I'll notice you and stop. There's definitely time for questions later, if you like. It is what it is. Also, this is a huge and complicated subject, so given the time frame, we're only kind of barely going to scratch the surface. If it's interesting enough, maybe there will be a part 2. And with that, let's start with a bit of a puzzle. So this is going to be a bit of code. It's going to be in Java. For those of you who don't do Java development, don't worry about it. Pretty much anyone who's done any software development in any language should be able to follow this particular bit of code because it's simple. So the first thing we're going to do is we're going to generate an array of bytes, 32K in size, and we're going to fill it in with random bytes. Now the second thing we're going to do is we're going to iterate over that array, and for every element that is positive, that is not less than 0, we're going to sum it, right? We're going to accumulate the value. Why? It doesn't matter. This is an artificial example. The point here is this. There's this algorithm, and the same algorithm applied to a different data set. In this case, we're going to take the exact same random byte array and sort it before we loop through it. And there's 3 questions that I want to pose to you. First being, which of these 2 versions, i.e. The version without the sort and the version with the sort, is faster? And by faster, I mean just the iteration, right? Not the setup. The second question is by how much, and the third question is why. So, any guesses?
Sorted faster.
The sorted is faster. Okay, so that's a reasonable guess. By how much?
A lot.
Twice as fast or a lot? Fair enough. And does anyone have a good guess why? If you already know the answer, like you've seen this before, then please keep quiet because it's not fun. But if you haven't, care to take a guess?
Prediction.
So I've heard branch prediction. What else?
15 times quicker.
What's that?
15 times quicker.
15 times quicker. And as for why branch prediction, any other takers? Any other guesses? CPU cache. Okay, fair enough. So we have a few decent theories. We know that the sorted version is probably going to be faster by 2 to 15, to a lot faster. And it might have to do with the CPU cache or with branching, which is a good thing because these are going to be most of the topics I'm going to be covering here. Okay, so the answer, unsurprisingly, this is, by the way, the results of a JMH benchmark. It's sort of the go-to framework for doing micro benchmarks in Java. And as you can see, the baseline version without the sorting takes literally 10 times as much CPU cycles as the sorted version. So yeah, there's an order of magnitude difference. So those of you who said twice, wrong. Those of you who said a lot, right. Those of you who said 15, almost right. Right? So this is actually a very, very big difference in performance. And it's the same algorithm. It's the same JITted code base, same assembly instruction, same CPU, same data size, same data set. Right? So everything is the same. It shouldn't be that big of a difference. Something must be going on. And for the rest of the talk, we're sort of going to be trying to figure out what that something is. So the first thing to realize is that CPUs are incredibly complex beasts, right? This is a microscope image of a CPU. You can see that it's crazy complex. And in case you were wondering which CPU this is a 286. This is a 30-year-old processor, and it's already so complex I can't figure out what the hell I'm looking at. Right? This is crazy complexity. But as with anything that is inherently complex, you can kind of abstract away some of the details and figure out a little bit about how it works, and that will make you better software engineers. With that, it is known that if you write your high-level code in like Java or C# or Python, whatever it is you're using, it ends up being compiled down to this horrible set of assembly instructions. This, by the way, is actually about 1/5 of the number of instructions that this particular code generates in Java. And obviously, when looking at this, the first thing that comes to mind is, what the hell am I looking at? What is somewhat less known, we're not actually going to delve deep into assembly code because that's kind of not the point. The point is that an assembly instruction doesn't actually reach the CPU by whatever means and gets atomically executed. It's not that simple. It's not like the CPU sees this instruction and goes, okay, I'll do that. Right? CPUs are complex. Like, as in any system, your software systems are not simple, right? They don't just take in HTTP requests and output cool data. It doesn't happen that way. There's a lot of complexity hidden behind that. Same with the CPU. So it is slightly less known that any instruction, any assembly instruction reaching the CPU undergoes a number of kind of execution phases. Right? There's a bunch of processing needs to get done before the result of the instruction actually applies. Now, this is a simplified view because every processor is a little bit different and has a different set of stages in different order. But fundamentally, you have these 5 steps, right? You need to fetch the instruction from main memory. You have to decode the instruction to figure out what it is that it's supposed to do. You have to dispatch it to the particular unit within the CPU responsible for actually executing that instruction. And then optionally, you may need to access main memory in order to get some input values in. And you might want to write back either to system memory or one of the CPU registers, right? These are the steps that are actually effectful, that actually do something useful. Every instruction goes through this process. Now let's digress a bit and take a quick high-level overview of what's in the CPU, right? What is the architecture of a CPU? This is once again, highly oversimplified diagram of an 8086. Once again, a 30-year-old processor that's ancient, that's 16-bit, that doesn't actually do all that much in today's standards. And you're not really expected to see the details, so don't worry about it. We'll kind of try and track through this. So what does a CPU do? Right? You have your CPU, it gets an instruction in. What is it actually responsible for? So as with the earlier 5 steps, it needs to read in the program. So there is a unit within the CPU responsible for talking to main memory and saying, give me the instruction at this address. This is generally called a bus unit. Right? The CPU speaks to other components in your computer through a CPU bus. There's a unit responsible for that. Next, it needs to actually figure out what the instruction is. That's the decode step. And for the 286, there's an instruction unit that's responsible for it. Next, it executes the instruction. This is the part where generally we're actually interested in. So you have your execution units, your LUs, and all of that stuff. We'll dig a little bit deeper into that. Then it needs to talk to memory again. So it actually goes through an address unit that deals with like address calculations and virtual memory, whatever the hell the CPU does to actually translate a memory address to something that it can send on the bus. And it might need to perform I/O, right? It might need to talk to peripherals, to talk to PCI cards, to your hard drive controller, whatever. This is incredibly complex, right? All of that stuff I just kind of glossed over is the source of immense complexity, and it's taken all of 50 years to get to the point where we are now, where we sort of take these things for granted and they work fast enough that we don't care. Once again, this is a 30-year-old processor. So while fundamentally not much has changed in how CPUs are kind of designed and architected, obviously, the details have changed radically over the last 30 years. Right. A word on execution units. The CPU actually has a number of discrete components kind of built into it, right? It's comprised of various classes or whatever you want to call it, various moving parts that each have their own responsibility. So an oversimplified view of this might be that you have 3 kind of fundamental units. You have your arithmetic logic unit, which is the piece of the CPU responsible for actually doing what we like to consider the CPU's actual work, right? Computation, Boolean algebra, control flow, like conditions, ifs, all that stuff, jumping around, basically doing the work of a central processing unit. Then you have your FPU, which deals with floating point numbers, floats, doubles, etc. And you have your memory management unit, which is responsible for translating addresses, virtual memory, paging, access control. Like if you try to write to an invalid address, you may get a seg fault. This is the unit that's responsible for figuring it out and kind of trapping the seg fault and issuing that instruction to the CPU. Right, so this is all kind of really, really basic stuff. And it's important to know how it's actually handled within the CPU, because that has ramifications on our code. More importantly, that has ramifications on how our code actually gets executed and how it operates within the CPU. So the first thing we need to consider is, we mentioned those 5 steps, right? Fetch, decode, execute, memory access, and write back. A naive solution might be to do them sequentially, right? You read an instruction, you go through the motions, you read the next one, you go through the motions again. This is not particularly useful because the latency here would be, for this kind of oversimplified CPU, would be 5 CPU cycles, right? A CPU cycle is the atomic unit in time in which the CPU actually does something. So it fetches, it decodes, it does execution, it does memory access. All of that stuff, for this simplified view, is 5 cycles. Your throughput, though, is crap, because it basically means for every 5 cycles, you get to execute 1 instruction. You get to actually do 1 unit of work, right? One sort of very, very simple optimization you could do as engineers on top of this would be to pipeline it, right? So maybe we can do some of these things in parallel. Maybe we can fetch the next instruction while the earlier one is being decoded. Maybe we can execute an instruction while the previous instruction is being, while the next instruction is being executed. So you have this kind of parallel process where it doesn't actually improve latency. It still takes 5 cycles for any given instruction to actually get executed, but you can do a lot more stuff. Right, so your overall throughput actually increases. Ideally, if you're fully parallelized and you can actually make use of the entire pipeline at the same time, then you get this 5-fold, in this case, increase in throughput, because you're actually retiring or executing 1 instruction in every CPU cycle, and the pipeline makes sure that the execution units are fed work to do in a timely manner. Now, pipelining might seem to be a very good kind of idea, right? It's very simple. It gets you quite a bit further, but it introduces some issues. And namely, there is something called the pipeline stall, right? When a pipeline stalls, it means that it stops in place and waits for something instead of doing work. This happens basically in a number of conditions, but there's 3 primary ones. One is memory access, which I'm not going to touch on this slide because there's a whole section dedicated to that in a little bit. But it may happen with branches. So consider this really, really ridiculously stupid if statement, right? Whereas if I is less than 0, then you increase I, otherwise you decrease I, right? Stupid artificial code, that's not the point. The point is that if you try and figure out what the CPU does here, there's a number of instructions that need to actually take place. So the first you have is a memory load, right? We need to load in the current value of I. Next, we have a test. We look at the value and we determine whether or not it's less than 0. Next, we need to have a conditional jump. If the value is 0, go to this part of the program. Is less than 0, sorry. If it's equal to or greater, then go to this part of the program. So what would be the next instruction, right? You wanna parallelize, you wanna pipeline, you wanna feed stuff into the CPU as fast as possible, but at this point, the CPU doesn't even know which way to go, right? So what happens? What happens is that you get a pipeline stall. The CPU literally waits for the result of the test and the conditional jump before it can actually figure out which is the next instruction that it needs to fetch. So your whole pipeline just stops for a while, and you've lost a few CPU cycles of useful work. The second condition in which this happens is with instruction level dependency. So you have these 2 instructions. The first increases the value of I. The second takes that value, adds 1 to it, and places it in a separate variable called x. Right? Once again, artificial code. That is, the point is to illustrate this. So we have one instruction that gets fetched, and that increments the memory address. Right? You don't actually have to, to separately load the value of I, increase it, and write it back. You generally have instructions to do all of these things at once. So this first instruction gets fetched, the next instruction gets fetched, and the first one gets decoded. That's the load from memory in order to read in the value of I and add 1 to it. The next instruction would be adding the 1, and the next instruction would be to store the new value in X. And so far, so good, but when it comes to actually doing the work, storing the value of X, suddenly you have this concurrency issue in your CPU, right? You have a memory access reading in the value of I, and you have a write back writing back the value, previously incremented value of I. Now, one of these needs to happen first, right? Some mechanism within the CPU has to guarantee that the order in which these things happen is correct. Otherwise, you get a race condition at the hardware level, which obviously isn't fun, right? So the next instruction, in the meantime, just waits, right? It can't do any work, so it stalls. This is a pipeline stall, and pipeline stalls generally also are called, by the way, pipeline bubbling. So if you come from more of an academic background, you may have run into this terminology instead. Pipeline stalls are basically responsible for slow execution of your code, right? A lot of, this is once again an oversimplification, but generally speaking, if your code runs slowly, then it's because it's stalling the CPU, and the CPU doesn't get to do as much work as it should. And with that, we're going to move to practical ramifications, right? So far, we've covered kind of the bare bones structure of a CPU, what it comprises, how it works. Now let's see how it affects our code at the high level. So the first thing to know is that memory is slow. Now, it might not seem that way, right? We've all been taught that memory access is fast and that it's almost negligible compared to I/O or disk access or all of that stuff. But within the confines of computation, like if what your code does is actual computation on the CPU, and all code does that. It might be deserializing JSON, and it might be compiling Scala, which takes a while, and it might be any other form of computation that you care to mention. Memory turns out to be an issue. So for a modern machine, by which I mean genuinely modern machine, right? An i7 Skylake processor at 4 gigahertz, sorry about that. RAM access tends to take completely random access to main memory, takes about 60 nanoseconds. Now, if you take a 4 gigahertz 64-bit CPU, the kind of commodity hardware that we all hopefully run on, assuming we're not running an ancient hardware, here's what happens. If the CPU has to wait for memory access to complete, it loses 250 cycles. And this is modern CPUs. For older CPUs, the number is way, way higher, right? So the CPU just basically wasted 250 opportunities to do computation just waiting for stuff to come back from main memory. The second thing that happens that if you just take this 60 nanosecond time and say, how many of these 60 nanosecond slots do I have in a second? How much data do I read for each kind of memory access, which for a 64-bit CPU would be generally 64 bits? You get random memory bandwidth of about 130 megabytes per second, which is just ridiculous, right? When you take a picture with your modern smartphone with its like 20 megapixel camera, you get like 30-ish megabytes of data just running through the system, right? And that happens in a split second. So obviously, something is going on here. Obviously, there is something that makes it fast, because this is just math, but the number is terrible. So engineers have been working for years and years and years to try to come up with various solutions to this issue. And the obvious solution that every single one of us has at least heard of and maybe even run into some ramifications of is a CPU cache, right? You have your CPU, you have your main memory. Accessing main memory takes about 60 nanoseconds, 62 in the case of a 4 gigahertz Skylake processor. Now, the cache is not this monolithic thing, it's a hierarchy, right? You have levels of cache. And the idea is that the faster it goes, like the closer it is to the actual computation, the more expensive it is to produce, the faster it has to run. So you have levels. You have your level 1 cache, which is always on the CPU, always running at full CPU speed. So it's very, very, very fast, but it's also expensive. So it tends to be small. So for modern processors, you might have 64K of level 1 cache, divided generally into 2 separate caches, one for instructions, one for data. Your level 2 cache might or might not be shared between your various CPU cores, but it's, for a modern processor, it might be 256K. The latency is what you should be looking at, because level 1 cache access latency is less than a nanosecond. It tends to be 4 to 5 CPU cycles, which is 2 orders of magnitude faster than RAM access. Then your level 2 cache takes 3 to 7 nanoseconds, and typically you might also have a level 3 cache that's shared between the CPU cores and takes 11 to 20 nanoseconds to access. Main memory, on the other hand, is humongous, but you need to go over the wire to access it, which takes time, 62 nanoseconds for a modern processor. Where this impacts your work, we'll see in a second, but first we need to understand a very simple thing, right? The CPU cache doesn't deal with bytes. That's just crazy. That's wasteful. It's impossible to manage. It deals with an atomic unit called a cache line. And a cache line on modern Intel CPUs or x86 CPUs tends to be about 64 bytes wide. So if you read 1 bit from main memory, actually your cache gets populated with 64 bytes. So the cost of reading in 64 bytes versus 1 bit is the same. The eviction policy, as with any sort of cache you might tend to use, is simple. It's least recently used, right? The memory that has been read from or written to most recently stays hot. The one that isn't, the cache line that isn't, gets thrown away. So sequential access is fast, and everyone knows that. But the reason why it's fast is actually that there is a number of reasons, but the biggest reason might be that there is a mechanism within the CPU called the prefetcher, whose sole responsibility is to have a look at your memory accesses and try to find patterns in them. Sorry about that. So if you're, say, processing a big chunk of memory, you might have already processed some of it, and you're working on your current iteration of your loop or whatever. The prefetcher has already noticed that you're accessing memory in a sequential pattern, and it reads in data ahead of time. It populates the cache ahead of time so that the CPU can continue its computation as quickly as possible. Does that make sense? Any questions up until this point? Right. So where can you see the ramifications of this architecture in your kind of day-to-day work? Now, this, you don't generally run into these things because for most of us doing application development, we're kind of working behind the scenes in server code or in client code. We have these high-level languages and high-level abstractions. We're usually I/O or network bound, not CPU bound. That being said, the libraries that we use are well aware of these ramifications and have been heavily optimized. Also, maybe you're in a different space. Last year's build stuff in this very room had Howard Chu giving a talk about the architecture of the Lightning Memory Map DB, which is one of those Berkeley DB competitors. So that is very, very low-level stuff, and they need to know these things very, very intimately and take them into account. So in our case, just to give an example, we have this image of a very odd cat. Let's say we want to rotate it by 90 degrees, right? This is actually a matrix transposition. So if you do any kind of computation with linear algebra and you transpose matrices and you multiply matrices, exactly the same effect. The algorithm for this is dead simple, right? You iterate over the rows, you iterate over the columns, you take a pixel at position X, row Y, column X, you place it in column Y, row X in the target image. Right, so this is just a very simple inner loop that doesn't do anything particularly fancy. As it turns out, this is very, very, very inefficient. Why is that? Because reads are sequential. right? You read left to right, you read a row of pixels, you read the next row of pixels, it's all sequential, it's all very nice. But you write not quite sequentially, right? You need to jump around in memory in order to actually write the result in. So that actually throws your caching system into thrashing, right? Because you need to read this cache line, and this cache line, and this cache line, and you have all these back and forths between parts of memory. The cache isn't really that effective in this case. So, by the way, the delta, like between the delta in memory access, like in the address of memory between iterations of a loop, is generally called a stride. And we have different strides for reads and writes. And unfortunately, because we're doing both at the same time, the worst case wins, right? We're reading and we're writing. So the slower of the two determines the result of your algorithm. So a word on cache-friendly algorithms. One kind of canonical way of dealing with this might be to use what is called the blocking or a tiling algorithm. This is really, really kind of basic stuff for anyone doing high-performance computing of any sort. What this means is that instead of actually dealing with your image as a whole, you split it up into blocks. So in this example, we have a very zoomed-in 16 by 16 pixel block, and we're going to process just that block, and then we're going to move to the next one. So the algorithm might look a little bit like this, which is actually very, very similar, right? We work in blocks, and for each block, we have the same computation that we did before. Now, the reason this is effective is because it limits the range of memory addresses that need to be hot in the CPU cache for any given chunk of computation, right? The entire image, you're processing the same amount of pixels, but you're doing it in a different order that maximizes the use of hot cache lines, and you're not thrashing around in main memory. If you're curious about the results, like how fast would this go, then we have the same benchmark. By the way, the sources for these benchmarks are all going to be there's going to be a link in the last slide, and you're also welcome to ask me any questions. So the naive version takes 43.8 milliseconds on my laptop to transpose a 4K resolution image of a cat, right? About 50 milliseconds. Then we have various tile sizes. We're running the blocking algorithm with 8 by 8 pixel tiles, 16 by 16, 48 by 48. And you can see that there are differences there, right? There's a sweet spot that depends on like the cache sizes and the latencies and all that stuff. So it would be different for every CPU. But even the worst performing version, which takes 48 by 48 pixels, is still over twice as fast as the naive version. Whereas the fastest version in this particular experiment is 2.37 times faster, just by taking the same computation and dividing it up a little bit differently. That is how important cache is to the performance of your code. We're done with caching. Any questions? Are you ready? Awesome. Okay, number 2, branching, those pesky branches. So fundamentally, a branch means I evaluate a condition, and based on the result of this condition, I go left or I go right. It's like a fork in the road, right? So which way should I go, right? As a CPU, I either wait for the result of the computation, in which case I stall and I waste valuable CPU resources, or maybe if I had some additional data, I could make a better guess. I could make better determination which direction I should go in. So I don't want to wait for the data, but I need it. So maybe I can take a guess, say, based on historic trends, right? I can take a look at a particular condition that happens often, say, within an inner loop. And maybe I can look at the results of prior computations and try to figure out a good guess of which way I can go. This might sound speculative, but it's actually a lot of the kind of performance-oriented stuff that your CPU does, and by the way, your VM, if you're writing in any high-level language today, is speculative. They take guesses. They try to amortize the cost of bad guesses over the lifetime of your program, and they try to maximize the benefit of good guesses. And obviously, they put in a lot of work to make the guesses better. So this is called branch prediction in modern CPUs. Now, branch prediction has been around for a while. It's gotten quite a bit of research and quite a bit of headway in the early 90s. What branch prediction does is it does two things concurrently. It speculates on which side of the branch execution will proceed, right? It takes a guess whether it should go left or right. Concurrently, it actually evaluates the condition because, like we said, the CPU might be able to do various things in parallel. So it can do both of these things at once. Now, you can think of it as a database transaction. You know, it's basically optimistic locking, right? You try something out, and if it fails, you roll back. And if it succeeds, you've committed. Now, if your success rate is high, then it means that you don't have to wait as much. So things run very, very fast. On the other hand, if you speculated wrong and you've picked the wrong branch, then you need to actually roll back the work that you've done. And the CPU does all of this for every single branch in hardware when your program runs on top of it. So, some of you already have guessed what the result is. I'm going to give you roughly 10 seconds to take a good guess as to why, you know, going back to our kind of original conundrum. Why is it that the pre-sorted version runs way faster by an order of magnitude, and also, you know, maybe try to think up an explanation for it. So, 10 seconds, go. That's okay, there's gonna be an explanation. I'm just giving you time to figure it out, hopefully. So, obviously, given the context, right, the culprit here is this if statement, is this condition, right? Now, this last part of the slide deck is going to be about why. And it's actually pretty simple to understand. So, we have our array of bytes with various values completely thrown at random. Now, suppose we actually sort it. So after sorting, we have our negative values on the one end and our positive values on the other. And this 0 in this case is kind of like a pivot point, because on the left side of this 0, you know for a fact that every single number is a negative number. And on the right side of the 0, every single element in the array is by definition either 0 or positive. So what we've done here is we've actually created the perfect conditions for branch prediction, right? The CPU actually starts looping through the array, and it looks at this and it says, okay, well, it's at the left side of the branch, cool, and it keeps track. Then it does the next one, the next one, the next one. And after a while, it figures out, well, you know, I can speculate pretty safely because this seems pretty consistent. And then it just kind of churns through everything as fast as, well, not humanly, but as fast as a CPU possibly could, until it reaches the 0. And then the condition turns. So you have, you know, you have your execution reach this point, then it wastes a bit of time kind of refiguring out where, you know, where the branch prediction ought to guess, right? It looks at historical trends, it says, okay, well, that's weird, something has changed. It takes it a few more elements to kind of figure out what the expected result is. And from this point on, it jumps always to the right branch, right? So this is, what would be the opposite of a pathological case? This is like the perfect opportunity for a branch prediction to increase the performance of your code. And that results in an order of magnitude difference in performance, which is desirable, right? You want that kind of performance out of your CPU. So this explains why we've seen what we've seen at the beginning of the talk. And at this point, I'm basically out of things to show you, but I hope you've just learned a little bit about how the CPU works and kind of what it can do for you and what it does to make your code run fast. And if there are any questions, I'd be happy to take them.
On the screen.
On screen, there are some questions. Let's see. I always hear that level 1 cache is expensive, but nobody ever says, why is it expensive? Is it made of unicorn blood or something? So it might be made of unicorn blood. I don't know what stuff Intel uses to make their CPUs nowadays. It might very well be. The reason level 1 cache is expensive is because it's on die, it's next to every other component of the CPU. It needs to run at full speed, like it needs to be as fast as the CPU in order to feed in data as fast as possible, which means that it needs to be kept small because it's running at full clock rate, and it's expensive because it's on the CPU die. So basically, anything you add to the CPU, it's silicon. There's a manufacturing process. It's kind of like you have a car and you have a feature on a car. Any feature, no matter how stupid, adds to the cost of the car. And some features add a lot, some features add a little. In this case, the level 1 cache would be a very expensive feature. I don't necessarily know why it would be more expensive than, say, an on-die level 2 or level 3 cache, but factually that is the case. I'm afraid I can't give a more kind of accurate response. Next question. By the way, if there are any questions from the audience here, raise your hands. You take priority. Yeah.
So I mean, I get why the branching is optimized and it's faster, but the sorting itself has to go through the whole array, and the branches for each element is probably optimized. But why does that not take so much time?
So the question was with respect to the branch prediction, the sorting, the pre-sorted version. Why is the sort not taking more time? It's because I might have kind of run through it a little bit fast, but the results are for the algorithm, not the setup. So I'm not taking them into account. Okay. The sort doesn't enter into it. By the way, when it comes to the effects of cache, there are actually interesting articles you might want to read about the difference in cache performance between different kind of sorting algorithms. So quicksort is kind of the go-to sorting algorithm, and it's general purpose, it's in place, it's stable, it's very fast. As it turns out, for some use cases, doing erratic sort, which is like an in-pass through the array, but without almost any random access, happens to actually be faster. So because you don't thrash around memory, and the cache is very, very effective. So even with sorting, in some cases it might actually be faster. The version with the sorting might actually be faster, even if we take sorting into account. So there's lots of ins and outs. Any other audience questions before we move back to the screen? Awesome. Next question. How much gap of performance is there between L1 cache and the CPU registers? If registers were in L1 cache, how much slower would the CPU go? So register access, I can't give you the details of why that is because, frankly, I don't know, right? This is for CPU engineers. The register file is very fast. Like it doesn't even take cycles as such. It's wired within the CPU so that access to registers is, for all practical purposes, instantaneous. Memory access actually needs a protocol for accessing the cache. So it takes 4 to 5 cycles, right? So fundamentally, accessing a CPU register is practically free. Accessing cache is very, very cheap, but it does have a cost associated with it. Beyond that, you'll have to ask a hardware engineer. I simply do not know. Next, this appears to be a response to a question. Next we have, are today's floating point units consistent throughout all new CPUs and isn't guaranteed to return the same result bitwise for operations with numbers? So I'm not sure what whoever asked this question means by consistent. FPUs generally follow very strict rules about how they deal with numbers. There's the IEEE 7.5 whatever standard that defines kind of the format of floating point numbers as we know them today, and defines the semantics of various computations. I don't know if you can expect, perfectly compatible bitwise results between different CPUs because, for some numbers you can represent the same number with different exponents and mantisas. So actually, you could have the exact same results from 2 CPUs that is not bitwise. Identical. So I don't know that I would necessarily trust that, but you shouldn't be doing bitwise comparison on floating point numbers anyway. That is a bad idea. Beyond that, well, they're consistent because things work and spaceships do not generally crash, usually. Next, cache fault sharing. That needs to always be covered in a caching discussion. Multi-core processing is a thing. So that is more of a comment than it is a question, and it's a fair comment. In this talk, I've kind of ignored the fact that processors have multiple cores. There are ramifications to that. So some cache and certainly memory is shared between CPUs, between the different cores in your CPU. False sharing is what happens when you accidentally do stuff on the same cache line, even though semantically you meant for two CPUs to do two different things. So one example of this is if you have a thread pool. Each thread does like a chunk of computation, but deals with counters. Like you have an array of counters, right? And you're counting words in a document or whatever using 4 threads on your 4 cores. But you're writing the counts to the same 4-element array. That array fits within a single cache line, which means that that cache line has to be shared between the different CPU cores, and they have to coordinate access to that cache line. And that is relatively expensive. That is false sharing in a nutshell. I hope that kind of makes sense. The reason why I've not covered it is simple. There's enough complexity within a single CPU. Multiple CPUs add a whole bunch of completely new and fascinating complexity to the mix. Any questions further? Audience? No? Okay. Anything else here? Is sort included in measurement? No. Hey, so we were calculating the sum of absolutes, or I think I missed something. Why was there an if at all? So you could, for this particular algorithm, you could use an instruction to, instead of checking, he's referring to the original question, which is this algorithm. So you could have the same effect if you used algebraic instructions. Like you could take the value in the element I of the data array and just calculate the absolute value of it. There's even a CPU instruction to do that and not have the condition at all. While that is true, that is not the point, because I could have said if I is greater than or equals to 7, and you would have had kind of the same effect, right? In which case, you could you can make this as complicated as you like. The bottom line is the same. And with that, I think we are done. So if there are no further questions, thank you very much for your time.